Welcome to Demystifying Math. In this lesson, we're going to be discussing optimization. Let's start with this problem. Suppose you wanted to have a vegetable garden and you were going to fence it in. You know that your vegetables are going to require at least 100 square feet of space. But what you want to do is kind of save some money on fencing. So you want to figure out what the dimensions would be so that you would have the least amount of fencing possible. Well, normally, and this is going to be a rectangular area, by the way, the area would be length times width. We're going to call it x times y, which means that our perimeter is going to be 2x plus 2y. Now, we do know that the area is 100, so we're going to set 100 equal to xy and isolate y. So 100 over x is equal to y, which is kind of like a boundary equation for us. So we're going to go ahead and graph it and draw a rectangle within the dimensions of that and the x and y axes. Okay, so here we have the curve 100 over x. Any x and y value that satisfy that equation are going to give us x times y equals 100. So what we've done is drawn point C on the curve, and then I just drew a rectangle that's bounded by the x and y axis and the curve. So here we have a square that's 10 by 10. 10 times 10 is 100, so our area is 100, and our perimeter is 40. Now suppose that we decided to have a rectangle that's 20 by, let's say, 20 by 5. Well, if it's 20 by 5, then that means that 20 times 5 is 100, so our area is still 100, and the perimeter is going to be 50. So when I have it as 20 by 5, I have more perimeter, which requires more fencing, than when I had it as a square, 10 by 10. Now, if we go ahead and look at all these possible ordered pairs on here, they're all going to give me an area of 100, but the perimeter is changing all the time. Now, let's go back up here. We could have it be taller, rather than shorter and longer. And you would see what our perimeter is here. So we're around 43 for our perimeter, going down to 42, still going down. Remember, we want to minimize the perimeter to minimize the fencing. And then we get to where it's a square and it's at 40. Now when I go beyond this square, notice that my perimeter is now increasing again. So we're getting the same rectangles, it's just kind of turned on their side down here. So it looks like when it's a square that we're going to have the least amount of fencing needed. So that would be at 10 by 10. So let's go back and prove this with calculus. Okay, so since it is the perimeter that we want to minimize, we're going to take the derivative of the perimeter equation. Now right now the perimeter equation is in terms of both x and y, so we want to change everything into x's. So what we're going to do is replace y with 100 over x, and then simplify it. So we have 2x plus 200 over x for our perimeter equation. Now everything's in terms of x. I'm just going to rewrite it a little bit as 200x to the negative 1 for the second term. Now I want to take the derivative of that perimeter equation. So taking the derivative, we get 2 minus 200x to the negative 2. Now what I want to do is find the critical points. So in order to find the critical points, I'm first going to rewrite this as one fraction. So I ended up with 2x squared minus 200 all over x squared. Now remember, your critical points are going to be whether your numerator or your denominator are equal to 0. So in other words, where your derivative is 0 or undefined. So we're going to set both of those, numerator and denominator, equal to 0. Now where we have x squared equal to 0, it's really not going to help us because it doesn't make any sense for one side of our fenced area to be 0. So we're going to leave that one alone. And we're going to concentrate on the 2x squared equals 200. So that gives us x equals 10. Now we would normally say plus or minus 10 because we took the square root, but again, doesn't make any sense for one side of a fenced-in area to be a negative length. So we're just going to take the positive 10. Now remember that you still have to check, even though you found the critical point at 10, you still have to check and make sure that it's a minimum point. So what we want to do is check for a sign change. So on each side of 10, I'm going to plug in a number to see if it changes from increasing to decreasing or from decreasing to increasing. So I chose a point below 10 at 1, and I got negative 198, which means that the graph of the perimeter is going to be decreasing on the left side of 10. Then I chose a point at 12, which is above 10, and I got out a positive number, which means that the graph of the perimeter is increasing on the right side of 10. So if your graph goes from decreasing to increasing, the critical point in between must be a low point, so it's a minimum point. So that minimizes our fencing. Now what we want to do is find our corresponding y value. So we're going to plug that into our equation for y, which is 100 over x. So that gives us out 10, and that's our 10 by 10 square that we were talking about earlier. So we would have the least amount of fencing possible when we have a 10 by 10 fenced area. Now, how much fencing do we need? We have to go back to our original perimeter equation and plug in x is 10, y is 10, and we get out our 40 that we expected to get out. So 40 feet of fencing is the least amount of fencing possible to have 100 square feet of area. Okay, let's try this problem. We have the graph of x squared, and we want to find the point that is closest to the point at 4 1/2 that we have drawn there. So we have this point D and this point xy. What we want to do is find the least amount of distance between those two points, where xy could be any point on the curve of x squared. Okay, so here we have our point xy and our point D. Now, what I'm going to do is kind of move xy along. You can see that the segment between D and xy is longer when you're further up on the x squared curve. So somewhere in there, there's going to be a point at which the distance between x, y, and D is the least. And that's the point that we want to find. Now here we're kind of going down, down, down. Let's see what happens here if it ever stops going down. Now you may think it's the horizontal distance, but it's not quite. Oh, look what happened there. Okay, so here we're at 2.99. It goes down to 2.95 and then back up to 2.696. So it's going to be somewhere in here around 2.95 units. It's going to be the least distance in between D and xy. So what we need to do is find out what those points, what the xy value are. So what we're going to do is use calculus to figure that out. Now a lot of times you think, oh, it's going to be the horizontal distance to the graph, but because the graph is curved, it's coming in closer to D in here somewhere and then coming back out again. So let's go prove this with calculus. Okay, so we're looking at the distance on the coordinate plane between 2 points. So the easiest way to do that is to use our distance formula. With our distance formula, we have an endpoint at xy and an endpoint at 4 1/2. So we're going to replace x2, y2 with xy, and we're going to replace x1, y1 with 4 1/2. Now, we want to be able to minimize the distance, so we need to turn everything into x's. But that's okay, because we have the equation f of x equals x squared, or y equals x squared. So we're just going to replace our y with x squared. Then we're going to FOIL everything out. And after we do that, you should see that the x squareds are going to cancel each other, and then we're going to simplify this. So it simplifies down to the square root of x to the 4th minus 8x plus 16 1/4. Now that's what we want to minimize, so that's what we want to take the derivative of. But let's reason through this and make our problem a little bit easier. If we minimize what's underneath the radical, that would also be minimizing the entire function with the radical. So what we're going to do here is focus in on what's under the radical and take the derivative of that. And that's going to give us an x value that's going to minimize that distance. So taking the derivative of that, we ended up with 4x to the 3rd minus 8. We're going to set that equal to 0 and isolate x. So I ended up with the cube root of 2, which is about 1.26. Now what we could do from there is figure out what our corresponding y value would be. So I plugged the cube root of 2 and squared it and got y, which is about 1.59. Now what we want to do is figure out what is that distance now that we have our x and our y values. So what we would do is take those x and y values and go back and plug it into our formula for the distance. All right, not just what's underneath, but we have to take the square root of it as well. So I ended up with 2.95, which is kind of what we expected to find from looking at our graph earlier. So that means that when x is 1.26 and y is 1.59, we have a minimum distance which is 2.95. Now, technically with calculus you should check and make sure that it is a minimum distance, not a maximum distance, right? So there's a couple ways you could do that. You could do look for a sign change on either side of square cube root of 2, or you could look at your second derivative. So let's look at our second derivative, and that's going to tell us the concavity of the graph. So our second derivative is 12x squared, and we're going to plug in the cube root of 2, and that gave me around 15, positive number. If it's a positive number, that means that the graph of the d function is concave up at x equal to cube root of 2. So if it's concave up, that means that we have a low point. So this is a minimum point on our graph, so we have proved everything that we need to prove here. Okay, let's go on to our next one. We have a rectangle that is bounded by both the x and y axes, and the graph of 4x plus 5y equals 20. So the first thing that you would do on this problem is to graph 4x plus 5y equals 20. So I would find my x and y intercepts, and they're at 5 and 4, and then graph it. Now remember that your rectangle is bounded by that line as well as the x and y axes. So this looks a lot like the first problem that we did. But remember with the first problem, we wanted to minimize perimeter to save money on fencing. With this one, we want to find the greatest area possible that we can fit a rectangle into this region here. Okay? So what we want to do is go ahead and isolate y. So that gives us negative 4/5 x plus 4. Now we did that because we want to find area. The area of this rectangle is going to be x times y. So let's go ahead and write our area formula. So it's x times the equation for y, which we simplified to negative 4/5 x squared plus 4x. Now because it's the area that we want to find the greatest of, we want to take the derivative of the area. So we're going to take the derivative of the area formula. And we get negative 8/5 x plus 4. Now we're going to set that equal to 0 to find our x value, our critical point. And we got 2.5. Now we need to also verify that that is a maximum point. So we're going to go ahead and take our second derivative, which we got as a negative. So the area formula in this case is always concave down. That means that the critical point that we found must be a maximum point. So we have x equals 2/5, and we need to figure out what our y value is. So we're going to plug 2/5 or 5/2 back into our equation for y, which was the negative 4/5 x plus 4. And that gave me out 2. So when x is 2.5 and y is 2, we have our maximum area. And then all we have to do is multiply them together to get the maximum area, which in this case would be 5. So 2.5 by 5 creates our greatest area. All right, thank you for tuning in to Demystifying Math.